When we are considering alkanes, alkenes and alkynes, alkynes will have the highest acidic character. Vicinal dihalides, that means the two halogen atoms will be on the adjacent carbon atoms. Geminal dihalides means both the halogen atoms will be present on the same carbon atom. Calcium carbonate, when it dissociates, you get calcium oxide and carbon dioxide. Now this calcium oxide, when it reacts with carbon, you will get calcium carbide and carbon monoxide. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in the last session, we finished with the chemical properties of alkenes, right? So we completely discussed about the preparations, physical properties as well as chemical properties of alkenes and alkanes, right? So today we are going to start with alkynes, right? So first we will be studying the nomenclature of alkynes, right? And then methods of preparation, chemical properties, and then the physical properties of alkynes. So we will be finishing alkynes today, right? So first let us begin by understanding what are alkynes. So we already studied what is alkenes, right? Alkenes are unsaturated hydrocarbons. So even alkynes are unsaturated hydrocarbons which contains at least one carbon-carbon triple bond, right? In alkenes it is double bond, in alkynes it is triple bond. So alkynes are unsaturated aliphatic hydrocarbons containing one carbon-carbon triple bond, and they are also called as acetylenes. This is another name for alkynes, right? It is also called as acetylenes, and the general formula is CnH2n minus 2, CnH2n minus 2. Right. So, for an alkane which is having two number of carbon atoms, C2, if we substitute in this equation, H2 into N. N, if you are taking the value as 2, it is 4. 4 minus 2, it is again 2. So, it will be C2H2. Same way we can calculate for any other alkynes as well. So, this is the general formula. So, I hope you remember the general formula for alkanes, alkenes as well as alkynes. Alkanes, it is CnH2n plus 2. Alkenes, it is CnH2n. And alkynes, it is CnH2n minus 2. Right. Okay. Now, let's move on to the nomenclature. So, the nomenclature is quite similar with what we have studied already for alkenes. So, in the case of alkanes, the suffix is ane. That means we end the name with ane, right? And then in case of alkenes, it was ene, right? And in the case of alkynes, it will be yne. Right. So, in trivial system, alkynes are named as derivatives of acetylene. In IUPAC system, replacing ane by yne, yne. Right. So, let's see the first one. Yes, as you can see here itself, the first member of the alkyne will contain two carbon atoms, right? Okay, so this is called as the trivial system name is acetylene, the IUPAC name is ethyne. So as you can see here, there are two carbon atoms, so the root word will be eth, right? And the suffix will be yne, so the name ethyne. Now moving on to the next one. How many carbon atoms are there? 3 carbon atoms, right? CH3, C triple bond, CH. Okay, so as you can see, from which direction we'll number, the triple bond gets more priority, right? So 1, 2, 3. This will be the order. So on the first carbon atom, you have the triple bond. Hence the name will be propyne. Okay, it will be propyne. Or else you can also write it as prop1-ine. Right. Now moving on to the next one. CH3, CH2, C triple bond, CH. How many carbon atoms are there? 4. So the root word will be but, right? So as you can see, from where I should number from this side, 1, 2, 3, 4, because the triple bond is present here. So the name will be butene or but1-ine, as you can see, but1-ine. Now the last one is CH3, C triple bond, CCH3. So the triple bond is present here, right, in the middle. Okay, so from either side we can number it. So if I am numbering from this direction, 1, 2, 3, 4, right? On the second carbon atom, you have the triple bond. Hence the name will be but2-ine, right? It will be but2-ine. So I hope that is clear, the IUPAC nomenclature. So the nomenclature rules we have already studied in organic chemistry. The same applies here as well, right? So if there is a triple bonded system in any other carbon atom, you have to mention the position of that as well. As you can see in this example, it is but2-ine, right? So the suffix will be ine in the case of alkynes, right? Now moving on to the next part, that is isomerism. So we have already studied the isomerism in alkanes as well as alkenes. So ethine and propyne have got only one structure. Ethine and propyne. What is ethine? C triple bond C, and on each side you have one hydrogen atom. So it is having only one structure. Same way propyne also. But there are two possible structures for butane. Okay. So one is but1-ine and the second one is but2-ine. Okay. Since these two compounds differ in their structures due to the position of the triple bond, they are known as position isomers. Okay. So let's take the example of butane. CH3, CH2, C triple bond CH, right? Okay, so in this case, as you can see, how many carbon atoms are there? 4. So this is a butane system, and you can see this is on the first carbon atom, right? On the first carbon atom, so the name is but1-ine. Now moving on to the next one, CH3, C triple bond C, CH3. So in this example, as you can see here, what is the difference between these two? The triple bond has shifted from this position to the next carbon atom. So this is an isomer, right? Okay. So what is the difference? Only the position of the triple bond has changed. So this is called as a position isomer. So but1-ine and but2-ine are position isomers because only the position of the triple bond has changed. So I hope that is clear. Now let's take the example of pentane. Okay, as you know, pentane means 5 carbon atom system, right? So this is pent1-ine. Okay, as you can see, it is on the first carbon atom. Triple bond is present. So 1, 2, 3, 4, 5 pentine. Now, if the triple bond shifts to the next carbon atom, you get another isomer, right? So it is 1, 2, 3, 4, 5 again, and the triple bond is present on the second carbon atom. So the IUPAC name will be pent2-ine. This is another isomer. Again, this is a position isomer, right? Only the triple bond position has changed. Now moving on to the next one. Right. Next one, what is the difference you can see here? The triple bond is on the first carbon atom, but one CH3 group is present as a branch now. Okay. As you can see here, okay, all other 4 carbon atoms is in the straight chain, but one CH3 group is brought as a branch here. So what is the name of this? Okay, we have already studied the IUPAC nomenclature rules, right? So according to the rules, we have to name the branch first. It is present on which carbon atom? Third carbon atom. So the name will be 3-methyl. Then again, the system is but now, not pent. The principal chain is but1-ine. Okay. Now this is also an isomer, but this is not a position isomer. This is a chain isomer, right? There is a difference in the branching here. Okay. So as you can see, structure 1 and 2 are position isomers. These 2 are position isomers. There is only difference in the position of the triple bond. And structure 1 and 3 or 2 and 3 are chain isomers. As you can see, there is a difference in the CH3 group present, right? So those are chain isomers. So you understood in alkynes, you can observe position as well as chain isomers. And also one more important point to remember, ethine as well as propyne is having only one structure, right? Moving on to the methods of preparation, which is very important. So the first one is from vicinal dihalides. So we have already discussed what is vicinal and geminal. Now dihalides means 2 halogens will be there. So for example, if we are taking CH2Cl and CH2Cl. So this is a vicinal dihalide. Vicinal means these 2 halogen groups, right? It is a dihalide, means you have 2 halogen groups or 2 halogen atoms which is present on the adjacent carbon atom. That means one chlorine atom is present on this carbon atom. Another will be present on the adjacent carbon atom. So such dihalides are called as vicinal dihalides. Now let's see, vicinal dihalides on treatment with alcoholic potassium hydroxide undergo dehydrohalogenation. It undergoes what? Dehydrohalogenation. That means we are going to remove HX, right? H and X, hydrohalogenation. Okay. One molecule of hydrogen halide is eliminated. What is hydrogen halide? HX itself, to form alkenyl halide, which on treatment with sodamide, NaNH2, gives alkyne. Okay, so first what is happening? Dehydrohalogenation will take place. One molecule of HX is removed. Then further it is reacted with sodium amide and finally you will obtain alkyne. So let's see the reaction here. Right, as you can see, CH2Br, what I have written there, the same thing. It's a vicinal dihalide. One halogen on this carbon atom, another on the adjacent carbon atom. It reacts with potassium hydroxide, alcoholic potassium hydroxide. That's why alcohol is written. So what will be happening here? The potassium and bromine KBr is removed, as well as one molecule of water is also removed. That means this OH and one H is removed. So what happens? You will get CH2 double bond CH2, and further when it reacts with sodamide, you will get alkynes. So this is the first method. Now moving on to the next one, from calcium carbide. Ethane is obtained by action of calcium carbide on water. Calcium carbide, what is calcium carbide? CaC2. So first let us understand how we can obtain calcium carbide. So calcium carbonate, when it dissociates, you get calcium oxide and carbon dioxide. Now this calcium oxide, when it reacts with carbon, you will get calcium carbide and carbon monoxide. So this is how you obtain calcium carbide. Now this calcium carbide, when it reacts with water, we will get calcium hydroxide as well as C2H2. What is C2H2? It is ethane, right? So we will get an alkyne. So I hope this preparation method is also clear. So you need to be knowing what is the preparation of calcium carbide, as well as from calcium carbide how we can prepare ethane. So now moving on to the chemical properties of alkynes. So first let us understand the acidic character of alkynes. So when we are considering alkanes, alkenes and alkynes, alkynes will have the highest acidic character. Now let's see, in alkynes, hydrogen attached to the carbon containing triple bond, it is sp hybridized, right? As you can see, it is C triple bond C. I'm taking the example of ethane. It is an sp hybridized carbon. Both the carbon atoms are sp hybridized, right? And they are acidic in nature. Hence, they can be easily replaced by metal or metal ions, forming the salts, okay, called sodium alkynides, okay, or else acetylides. So what does that mean? Yes, as it is having acidic character, when it reacts with any metal, you will get a salt of it, sodium salt of it. So this is what it means, okay. So why is the acidic character, or why alkynes are having an acidic character? Because the carbon is sp hybridized and the hydrogen atom can be easily replaced by another metal. So let's take the example first. This is an alkane here, and when it reacts with sodium, you will get sodium acetylide. That is a sodium salt, okay. That means what you can see here, this hydrogen will be replaced by sodium and hydrogen gas will be liberated. Another example, let's take, it is ethane. Ethane reacts with two molecules of sodium. What happens here? Right, this hydrogen as well as this hydrogen is involved in the triple bond, right? So both of this can be replaced. So you'll get one sodium here, and hydrogen gas will be liberated. So now let's take another example of sodamide. Again, we are taking propane here. CH3, C triple bond, CH. So this is propane. Propane reacts with sodamide. So what happens? Which hydrogen atom will be replaced? Any hydrogen atom here will be replaced? No. It is not a part of the triple bond. So this hydrogen atom will be replaced and you will get a sodium here by the liberation of ammonia. So this proves the acidic character of alkynes. Now moving on to the next one, addition reactions. Okay, so alkynes, we are going to study about the different addition reactions. So we have already discussed this in alkenes as well as alkanes, right? So first what we are going to do, addition of hydrogen. So you already know in alkenes also, when we were studying chemical reactions, when we are adding hydrogen to alkenes, what happens? We obtain alkanes, right? So I hope you remember the order that I have taught you. Alkynes, then alkenes, and then you have alkanes. Right. So what happens? From alkynes, you can obtain alkenes first, right? By adding hydrogen. Now, if you add hydrogen further to alkenes, you will obtain alkynes. Okay. So let's see. Alkynes readily reacts with hydrogen in the presence of platinum, palladium or nickel catalyst to form initially alkenes and then alkanes. So if you are continuing this process, you will obtain alkanes. So it is also called as catalytic hydrogenation, right? Hydrogenation means addition of hydrogen in the presence of catalyst. So let's take the example here. General example, it's an alkane to which hydrogen is added in the presence of nickel, platinum or palladium. Another important point, if nickel is present at a high temperature, we have to use it. It doesn't react under, or it doesn't act as a catalyst under normal temperatures, right? So what happens here? Hydrogen will be added on the either side. You can easily understand in that way. So what happens? You will get R as you can see. Okay, so it will be RCH double bond CH2, right? RCH double bond CH2, right? So what happens to the triple bond? We are adding something, right? So the triple bond will break into double bond. Again, we are further reacting it with in the catalyst nickel, and at high temperatures, what happens again? One hydrogen will be added on each side. So what you will get? RCH2 single bond CH3, right? So what is that? The final product you are obtaining? It is an alkyne. Okay, so from alkynes, by adding hydrogen, you will get alkenes first, further alkanes, right? So let's take the example of ethyne here, to which we are adding hydrogen in presence of platinum, palladium or nickel. First, one hydrogen will be added on each side. So you'll get CH2 double bond CH2. Again, one more molecule of hydrogen. So we'll get CH3, CH3. So from ethyne, we obtain ethane, right? Okay. Now the next one is addition of halogens, or also called as halogenation. Okay, so alkynes reacts with chlorine or bromine in the presence of inert solvent like CCl4, carbon tetrachloride, to form dihalides and tetrahalides. First it will form dihalides, then it will form tetrahalides. So let's take the example of propine here, to which we are adding bromine first. Br2 we are adding. So what happens? One molecule of Br will be attached here, another molecule of bromine will be attached on the other side. As you can see, it is CH3, C triple bond CH, to which we are adding bromine. So what happens? One bromine will be attached here, one bromine will be attached here. Right. So what happens to the triple bond? It will become double bond. So that is what you can observe here. Now further, if we are adding one more molecule of bromine, what happens here? Again, to this, if you are adding one more, another bromine will be added here, another bromine will be added here, and this triple bond will become a single bond. So that is what you can see here. Okay. So it will be CH3, C, Br, Br, CH, Br, Br. Right. Okay. So first you will get 1,2-dibromopropane. Then it will be further substituted by 2 more bromine atoms. That's it. Clear? Now moving on to the next one, that is addition of hydrogen halide. HX we are going to add. Alkynes reacts with 2 molecules of hydrogen halides to form geminal dihalides. So we already studied vicinal dihalides. That means the 2 halogen atoms will be on the adjacent carbon atoms. Geminal dihalides means both the halogen atoms will be present on the same carbon atom, in which 2 halogens are attached to the same carbon atom, right? Okay, and addition is governed by Markovnikov rule. So we already know what is Markovnikov rule. If we are adding hydrogen halide, that means HX, the negative part is the halogen, right? So the negative part will be attached to the carbon atom having lesser number of carbon atoms, right? So let's take this example of ethyne, to which we are adding HBr. So Br is the negative part of the adentum. So this will get attached to the carbon atom having less number of hydrogen atoms. But in this case, it is a symmetric alkyne. So there is no confusion. To one carbon atom, you can add hydrogen. To another carbon atom, you can add bromine. So you'll get CH2 double bond CHBr. That means to this carbon atom, we have added the hydrogen. To this carbon atom, we have added the bromine. So this is the product that we are going to obtain. Now, further we are adding one more molecule of HBr. One more molecule of HBr if we are adding. Now it goes according to the Markovnikov rule. So what happens here? We have HBr. To which carbon atom the bromine will go? As you can compare these 2 carbon atoms, which is having lesser number of hydrogen. Yes, this is this carbon atom. So the bromine will get attached to this carbon atom and hydrogen will go to the other carbon atom. So you will get CH3 single bond CH and 2 Br2 will be there. Okay, so I hope that is clear. Right. Now let's take the example of propine, to which we are adding HBr. So here itself, we have to apply the Markovnikov rule. So as you can see here, in which carbon atom the number of hydrogen atom is less? Yes, this one. So the Br will get attached here. So as you can see, it is CH3, CBr, double bond CH2. Right. Hydrogen will get attached here. Right. Now further we are adding one more molecule. What happens? Yes. What happens here? Now the next molecule, bromine, will get attached to this carbon atom. It is having lesser number, right? So you will get the next bromine atom also here and CH3. So you will get dibromopropane. So I hope this is clear, right? So what you have to remember, it goes according to the Markovnikov rule. Next one is addition of water. Alkynes add on water molecule when treated with dilute sulfuric acid at 60 degrees Celsius in the presence of mercuric sulfate catalyst to give an aldehyde or ketone. Okay, so even addition of water happens according to Markovnikov rule. So what is present here? It will be treated in the presence of dilute sulfuric acid and also in the presence of mercuric sulfate catalyst. You will obtain either an aldehyde or ketone. So let's understand the reaction. We have taken ethyne here. So what is water actually? It is made of H plus and OH minus, right? So again, OH minus, it is the negative part of the addendum which get attached to the carbon atom having lesser number of hydrogen atom. So in this case, no confusion because it is symmetric. So in the presence of mercuric sulfate and dilute sulfuric acid, what happens? Yes, as you can see here, the OH is getting attached to this carbon atom. That is what is represented here, and hydrogen here. So you will get CH2, COH, and this H is already there. So in the next step, what happens is isomerization will take place and this hydrogen will be shifted here and this will become a double bond. Isomerization will take place and you will get CH3. This hydrogen to here, CH3, and then you have C double bond O H. Now what is this? Which functional group it is? CHO. It is aldehyde, right? So you will get ethanol, right? Understood? Now moving on to the next example, which is of propine, to which we are adding water in presence of mercuric sulfate and dilute sulfuric acid. So now again we have to consider Markovnikov rule. The negative part will get attached to carbon having lesser number of hydrogen atom. So OH will go here, H will go here. So what you will get? CH3COH double bond CH2. Again isomerization will take place. This hydrogen will go here and this will become a double bond. The double bond will shift here. So what is that you are going to get? CH3, C double bond or CH3. What is this? It is a ketone, right? So either you will get an aldehyde or ketone. Okay, so this is about addition of water. Now moving on to the next one, that is polymerization, in which you have two types. One is linear polymerization and cyclic polymerization. So linear polymerization you have already studied in alkanes. So let's see, under suitable conditions, linear polymerization of ethane take place to produce polyacetylene or polyethylene. And thin film of polyacetylene can be used as electrodes in batteries, and this is used as electrodes in batteries. These films are good conductors, lighter and cheaper than metal conductors. So they are used as conductors and it's also used in batteries, right? So let's see the reaction. Ethane, 3 molecules of ethane, it will form polyethylene. So I hope this is clear. It will form, this is a monomer which will be repeated n times to form a polymer. Okay, so I hope that is clear. Now moving on to the next one, that is cyclic polymerization. Alkynes, when passed over red hot tube polymerize to give aromatic hydrocarbon. So as you can see, this is a chemical property of alkyne that it undergoes cyclic polymerization in presence of red hot iron tube to form, yes, aromatic hydrocarbon. Now in the next session we are going to study about aromatic hydrocarbons, where this is used as a preparation for aromatic hydrocarbon. So you have to link in such a way and study. This is a chemical property of alkyne which is used as a method of preparation for aromatic hydrocarbon. So as you can see here, ethane on passing through red hot iron tube at 873 Kelvin undergoes cyclic polymerization. So we are taking 3 molecules of ethane here. 1 molecule of ethane, second one, third one, 3 molecules of ethane. When passed through red hot iron tube, what we are getting? Yes, this is benzene, right? We get an aromatic hydrocarbon which is benzene. So this is cyclic polymerization. This was linear polymerization. So as it is undergoing cyclic polymerization, you will obtain a cyclic structure, right? So what is that you are obtaining? It is a benzene, right? Okay. Now moving on to the physical properties of alkynes. First 3 members are gases. It's quite similar with what we have studied for alkanes and alkenes. The next 3 members are liquid and the higher ones are solids. As the molecular mass keep on increasing, it becomes solid in nature. The first few are gases, the next few are liquids and the higher ones are solids. Now, ethane has a characteristic odor. It has a characteristic smell and others are odorless. Ethane is the first alkyne, right? Others are odorless. Now, they have low density and hence are insoluble in water but are soluble in organic solvents. So this is quite similar with alkanes and alkenes. They are not soluble in water. That is, they are insoluble in water, but they are soluble in organic solvents. So I hope the concepts that we have discussed in this session is clear for you. So we have completed the methods of preparation, physical properties as well as chemical properties of alkynes. So in the next session, we are going to discuss about the aromatic hydrocarbons. Okay. So I hope the class was clear for you. So that's all for today. Thank you.